Welcome back to this unit named Polymers, and this is the fourth lecture in this unit, and this will be the last lecture on polymers. So, if you go back and just recall what we have been discussing in our last lecture, we basically were discussing some of the synthetic processes of some of the common polymers, and just recap for one minute. We discussed the synthesis of polyethylene or polythene, and polyethylene could be two types: low density polyethylene or LDPE, sometimes is also written as LDP. Just is a radical polymerization of ethylene at high pressure, and the temperature range it is mentioned here. And because it is a radical polymerization, I explained in the last class that it produces long branches, and as a result the packing between the polymer chains is not very high. As a result, it basically the low density, it results in low density polymer. In the other case, which is high density polyethylene or HDP or HDPE, in this case we use a special catalyst which is discovered by Ziegler and Natta, and for which they got Nobel Prize, as I mentioned in the last lecture. And it is done in presence of this catalyst in the temperature range and little high pressure, and in this case you get it produces a linear polymers, and as a result the polymer chains can pack well, and we get a high density polymer material. The second resin we discussed was, or polymer we discussed was polytetrafluoroethylene. In short, it is written as PTFE, and sometimes it is called Teflon. Basically, the monomer is tetrafluoroethylene, and in presence of catalyst at high pressure, it basically produces polytetrafluoroethylene. The third we discussed was polyacrylonitrile, in short PAN. In this case, in presence of peroxide catalyst, the acrylonitrile monomer is polymerized. These are addition polymers. So, and a chain growth polymerization mechanism by which it forms polyacrylonitrile. And as I also mentioned in the last lecture, that the polyacrylonitrile is not often as a homopolymer. Generally, it is used along with styrene, and by basically a styrene acrylonitrile copolymers are made, and which are used more frequently than the homopolymer. The fourth polymer we discussed in last lecture was polyamides, which are commonly known as nylon, and there are basically three ways we can make. We can take a diamine and plus a diacids, and we can do direct amidation reaction between these two and form a polyamide, or you can take a amino carboxylic acids, and basically this contains two different functional groups. So, we can do self condensation among these two, and we can get the polyamide as well. The third option, we can get a cyclic amides and then perform a ring opening polymerization, where this ring opens up and the next monomer gets added in presence of catalyst, maybe acid catalysis, and you can get polyamides as well. And as I also mentioned that the name nylon are used commonly for this, and the nylons numbers are, because it will come with some number, and that depends on the number of carbon atoms in the diamine or a diacid. So, if you have a 6 carbon here, 6 carbon here, then it will be 6 nylon 6, and in this case if you have just a 6 here, 6 carbon amino acid converted to a polyamide by self condensation, then it will be just nylon 6. So, you can just recall the discussion we had on polyamides in last class. So, we will proceed our discussion on the synthesis of common polymers, and next polymer we will look after or just introduce you is the polyesters. You know, polyesters, as you can imagine that it will have ester group in the backbone. So, that is polyester, and again like polyamides you can have the three methods like direct esterification of diol and diacid produce a polyester, or you can have a hydroxycarboxylic acid and do a self condensation and get a polyester, or you can get a cyclic ester monomer which are lactones and then do a ring opening polymerization and get the polyamides, sorry, polyester in this case. Now, the most common polyesters which are used in market is synthesized from this, which we discussed earlier as well. This is terephthalic acid and this is ethylene glycol. In presence of catalysts, mostly acid catalyst at high temperature, it generates this polyester. Now, unlike the polyamides, this reaction is not very fast or very feasible reaction, actually it is a reversible reaction. So, to get this polyesters form effectively, you have to increase the temperature, so make it a higher temperature, so the reaction happen fast, and we also have to apply low pressure or vacuum and take out this water from system, so that the equilibrium or the reversible reaction proceeds toward product side. So, basically in this case we to make this polymer product feasible, we have to do in presence of catalyst, mostly acid catalyst, and then use a high temperature, and we have to take these acids which is a byproduct or a condensate from this reaction, take out. And the name of this polymer is polyethylene terephthalate. Now, you can know if you just do a reaction of in your organic chemistry nomenclature, if you take a acetic acid plus say ethyl alcohol C2H5OH, now the ester you get there you call this as a ethyl acetate. Now, similarly, in this case basically we have instead of acetic acid example we gave last time, we have a terephthalic acid and in this ethylene glycol. That is why we are naming ethylene terephthalate, and obviously it is a polymer. So, we are adding the name polymer besides this, and you put a bracket in this name. So, that is why the name is polyethylene terephthalate PET. Now, you will find in books or some texts that these are also named as like Dacron, Terylene, Mylar, etc., etc. Now, these are not the scientific names. These terms Dacron, Terylene, Mylar, these are called what is called trade names. Trade names. Now, what is trade names? Now, if you have a fever, what you take a paracetamol tablet, which is you buy as a Calpol or Crocin. So, if doctor prescribes you as a Calpol or a Crocin, now, but these Calpol and Crocin, these are the trade name, these are the name of the product, but the actual ingredient in this case is paracetamol. Similarly, in this case the polyethylene terephthalate is the polymer, but when it is marketed as a product, the companies will name is the different companies will have different name like Dacron, Terylene, Mylar. So, actually the question should not be asked based on this trade name, this should be asked on based on the your actual scientific name. So, you know the different and like nylons and the other names Teflon, those are also the trade names. The The scientific names we talked about, like in case of nylon 6,6, the hexamethylene adipamide, those are actually the scientific name, and then nylon 6,6, and these are actually a trade names, and we and the Teflon is also a trade name. So, so you know what is the difference between trade name and the actual scientific name, and you should actually remember and understand how the scientific naming of polymers happen. Now, in this case we have seen this reaction is not very feasible, as we said. So, we require high temperature and we have to take out the water. To make this more feasible, sometimes instead of dicarboxylic acid, we can use acid chloride, diacid chloride, and react with diol. In this case, you will get polyester plus HCl as a byproduct. You can also use methyl ester, like if I write this way, plus again the diol. You also will get a polyester, and in this case you will get methanol as a byproduct. So, these are the other ways you can make instead of using directly diacids, you can make this diacid chloride or dimethyl esters. So, in this case the reaction becomes more feasible, and in practice sometimes these are practically used in commercial plants. Now, in terms of properties of polyethylene terephthalate fibers, or say Dacron fibers or terylene fibers, these are having good abrasion resistance, good chemical, hydrolytic and solvent resistance, and it has outstanding crease resistance, which makes these fibers applicable for use for wrinkle free clothes. Now, if you go in a buy clothes, you always ask what the material is made up of, and sometimes you will get answer about this is made up of polyesters. And when you talk about polyesters, is mainly these PET fibers is what used in making clothes, and as a result sometimes you don't like to buy polyester clothes. So, in that case some of the companies, they actually mix these PET fibers or the polyethylene terephthalate fibers along with cotton or cellulose fibers, and make a mix of that and make clothes out of those mix of cellulose or cotton and PET fibers. So, next we will talk about, so we had now what 5, now we will have 6, number 6 we will talk about phenol formaldehyde polymers. These are actually bakelite and related polymers. It is also generically called phenolics. Now, this, as I mentioned earlier, this is the first completely synthetic polymer that was introduced in market. It was 1907, and this is made by a condensation reaction between phenol and formaldehyde. In presence of say acid catalyst or a base, and you get a mixture of product, ortho para mixture. At the first step you can get a different mixture of ortho para product. CH2, these are CH2OH, in case you are not able to read this properly, these are CH2OH. So, basically you can have a just ortho para and 3 substituted CH2OH in 3 substitute, and this reaction rate depends on the pH of the medium, and actually the it is a lower pH and a higher pH, the reaction rate goes up. So, basically you want to have a acidic medium or a alkalic medium, and you can take any of these things, and we will take example of this ortho substituted product which undergo self condensation among itself to produce polymer. So, you can use this, this is the product and this is called Novalec. You can imagine you can take also the other two and make polymers out of this, and this exact composition of this reaction depends upon the pH and the temperature of the medium, and the ratio of phenol and formaldehyde, ratio of phenol and formaldehyde, and other reaction conditions. These are the things which basically determined what is the exact composition of the reactants. And now, this Novalec is basically cross linked, or basically which we called curing, the process called curing, which is nothing but a cross linking reaction when it is heated with formaldehyde, and you actually get a cross link product. I can write here, it is a this. You can imagine that you basically making a cross linking product where you extend it in all the directions, this direction, this direction, this direction, this is the. So, this is a cross link product, and as a result this is infusible. So, you cannot basically recycle this product, and this product is also known as bakelite. Now, so this step where you basically cross link this Novalec resin by heating with the formulating is called a curing process. Is basically nothing, is a cross linking reaction. Now, sometimes instead of formaldehyde, which we here used a formaldehyde as a cross linking agent, we can sometimes use other cross linking agents like hexamethylene tetraamine, which is obtained from basically 6 moles of formaldehyde plus 4 moles of ammonia. Now, in this case, in addition to the cross linking linkages which we saw in the I showed in the last example, methylene cross linking So, instead of this is a methylene cross linking, we had this the example I showed you in the last page. You can, in addition to these, you can also have the other cross linking, like the one I am showing it, writing it now. So, you can have this type of cross linking as well. This is benzyl amine, cross linking. Now, these products, as you can see, this is a cross link product and infusible product. So, they will be having good resistance to impact, solvents, moisture, and they also have high strength and dimensional properties. As a result, they are used in several applications like electrical switches, combs, handle of various utensils, and so on. There are many applications you can imagine for this application, this compound. So, these are phenolics, as I said, is a reaction between phenol and formaldehyde. So, we will quickly move to the next one, which we will talk about as aminoplastics or polymers. In this case, we have formaldehyde reacting with either urea, giving some product. Another common example is melamine. In the resin between melamine and formaldehyde, what is used in this melamine utensils. So, you get again cross link product, and reaction is controlled by reaction controlled by pH and temperature of the medium. And the reaction is stopped when by bringing the reaction to the pH, cooling down the temperature and bringing the pH to near to the neutral pH. Now, the reaction, say I will show you this reaction, formaldehyde with melamine, which is very commonly used in making the utensils, as I said. First step, it will be like pre-polymer or intermediate pre-polymer or intermediate product, just like the phenol formaldehyde case, product, intermediate product, and then we will cross link by heating in presence of added acid catalyst. which basically cross link these polymers, and you get I will write this just the structure. So, that is the repeating unit. So, you this is a melamine melamine formaldehyde polymer, or in short melamine polymer, which basically are used in preparation of that coating the utensils which we commonly use. And in terms of application, this melanin also I do not want to write. So, basically okay, we do not need to write too many applications. Basically, you know this is very common, the melanin utensils you use. Okay, so, we basically has given 7 type of example and the synthesis process and some applications of them. So, next we will move. Before I move, I just wanted to show the there are other examples in your book. This is a copied from your NCERT book. So, there are other example given in the book. So, you please go through the polymers, the monomers, their structures and their uses. This is just you have the information. So, you have to remember the structure, the name of the polymer, monomer and their uses. So, please read this from book and remember, try to remember some of the structure and names of the polymer and their use. Ethylene. So, next what we will do, we will discuss the next topic, which is about rubber. Now, obviously, rubber, when you talk about it must be elastomer, where basically most common is the rubber band, where you basically stretch a rubber band, you can stretch it easily, and then when you stretch a rubber band, you can easily stretch, and then when you leave this, it will come back to the original dimension because of its elasticity. So, that is what we mostly associated about rubber. So, they are basically elastomer. And the use of rubber is from a long time ago, about 16th century people were using rubbers for making playing balls or waterproof clothings and erasers and all these things. And about 19th century where the technology of rubber started. And the technology was started because initially rubber had lot of problems. Rubber would get basically it will soften and gets sticky at warm temperature, at higher temperature, and when you bring the temperature, the rubber would become hard and brittle. So, these are the, and it will soluble in nonpolar solvent. So, these are the some of the reason why the rubber has a did not have applications or in many ways it could not basically expand its applications. So, in 19th century with the discovery of vulcanization is what when the rubber gets actually the application of rubber expanded in many areas. So, it was discovery of vulcanization of rubber. It was discovered by the vulcanization of rubber by using sulfur. And it was discovered by Charles Goodyear. You have probably heard Goodyear tire and it was done on long back 1839. in USA, and he filed patent, and which was granted. The patent was granted in 1844. So, by doing the vulcanization, what happened? The elastic properties was improved, elastic properties were improved, and tackiness was eliminated. Now, at the same time, there is another scientist, Thomas Hancock, in London, who also discovered similar vulcanization method, and he also filed patent at 1843. This is the filing year, and it was issued. The patent was granted, which was granted. The patent was granted after the Goodyear's patent at 1844. The first patent was to Charles Goodyear, and next was to this Thomas Hancock. And then in 1851, Goodyear's brother, Charles Goodyear's brother Nelson Goodyear, he basically improved the vulcanization process by using a large amount of sulfur, and which basically makes a hard polymer, hard rubber material, which were more useful and probably used for tire material. The first rubber which was obviously useful and utilized was natural rubber. We can write just NR for natural rubber, and natural rubbers is obtained, it is milky white. You probably have seen, if you have seen a rubber tree, it is a milky white latex which contained colloidal dispersion of rubber hydrocarbons, or you can call whatever particles. So, this is obtained from the bark of rubber tree. You know, if you probably visited Kerala, or sometimes you probably have seen the rubber trees, then from the bark you can get this milky white coming out, and you can get natural rubber from bark of the rubber trees, which are rubber trees are basically abundant in the Southeast Asia region like India, Sri Lanka, Indonesia, Malaysia, or in South America. And it basically useful, and the structure, if you look at the structure of the natural rubber, its chemical structure is like this. This is natural polymer. Obviously, we got the polymer. It is not that we had synthesized the polymer in the lab or plant. So, the polymer was obtained, and then structure was analyzed, and it was found like this. So, you can consider this is the repeating unit of the polymer. So, if you look at this polymer, you can see that this is a polymer you obtained. So, it is not that we have you are basically synthesizing a polymer from monomer, but if you think that this is, if you have to name that, generally how polymers are named, the polymers are named just adding poly and the monomer from which the polymers are formed. So, if you talk about ethylene is the monomer, we write polyethylene. Vinyl chloride is the polymer, so we write polyvinyl chloride. Polystyrene is the monomer, so we write polystyrene. If you ethylene glycol and terephthalic acid is your polymer and you obtain ester from that, we write polyethylene terephthalate. So, how do you name polymers? Is basically add the term poly and then the monomer or the repeat unit from which you got the polymer. So, basically we have this polymer now. So, if you want to name this, we have to imagine from which monomer we can synthesize or theoretically which form monomer it was synthesized and what is the structure here. Now, you can see there is a double bond here. So, as you have seen, you know that if there is a double bond, there could be two possibilities, there is a cis configuration or a trans configuration, and in this case you can see this is a cis configuration. So, we can think that this is a cis configuration, and what is the monomer, probably it is obtained. We can think that this is obtained from this monomer. So, this is a single bond, not double bond. So, if we think about this is the monomer, then we can think about a initiator which can react and you get the double bond here and you get the active center here. So, you get from here you get I CH2 . So, this is the active center, it can react with further this monomer and you can get this polymer. So, we can imagine that this is the monomer for this polymer, and what is the name of this? This is a 1,3,2-methyl 1,3-butadiene. Okay. So, basically we can think this is a monomer which is a 2-methyl 1,3-butadiene. Now, the attack in this case this polymer is through first carbon and fourth carbon. So, we are writing cis 1,4 poly 2-methyl 1,3-butadiene. So, this is the name of this polymer, natural polymer, and this 2-methyl 1,3-butadiene is also commonly written as isoprene. You can, I hope you understood why it is 1,4, because sometimes you can just add here, the active center will be here and you can make a polymer with this. So, that will be a 1,2 addition. You can have the polymer made through this only using this double bond. So, that will be a 3,4 addition, and in this case it is a 1,4 addition. So, that is why you are writing, because the cis configuration we are writing cis 1,4 poly 2-methyl 1,3-butadiene, and 2-methyl 1,3-butadiene is also written as sometimes polyisoprene. So, the polymer natural is also sometimes written as cis 1,4 polyisoprene. Now, these have very weak interactions between the molecules, and because of the cis configuration you can imagine that the polymer chain when it grows it coils up, and when it is coils up, what happened, you can stretch, while you stretch you basically you gives the retractive force and you get the elasticity because of the coil configuration. And these double bonds also help us further doing chemical reactions on the double bonds. which is what the vulcanization step is used to do. So, we will now learn what is vulcanization. Z or S, whatever you can write. Now, why do we require vulcanization of rubber? This natural rubber becomes soft, as I mentioned, soft and sticky at greater than 335 K. It becomes hard and brittle less than 283 K, and this limits their application, and it at low temperature is also a high water absorption capacity, and this is soluble in nonpolar solvents, and it is not resistant. So, non-resistance to resistant to attack to oxidizing, because of the double bond it can easily oxidize. So, basically it is not resistant to the oxidizing agents, which makes their use limited. The natural rubber is applications got limited, and that is the reason we require to cross link this rubber, and that is done using sulfur as a cross linker, and that is what called vulcanization step. So, you take the raw rubber, maybe I can do it in the next page. So, vulcanization is you take the raw rubber plus sulfur plus an appropriate additive, which basically accelerate this cross linking process. I am not going in the details of what these additives are, but an appropriate additive which basically helps in accelerating this this cross linking reaction. You heat it up, generally temperature is 273 to 415 K, and you have to keep it for, it is done for long hours. So, it takes time, and the amount of sulfur is small, probably between 1 to 5% in general case, but it could be in even smaller or even higher if required, and you get this cross linking different cross linking products, and we just writing few structures. Remember, the base structure was polyisoprene, 2-methyl 1,3-butadiene. This is one possibility. The other possibility could be so, these are basically cross linking happens between two natural rubber chains, which are basically nothing but polyisoprene, cis-1,4 polyisoprene, what we talked about earlier. And in case of if you add 5% rubber sulfur, sulfur in it basically cross link heavily, and it can be used for tire application. So, basically tire rubber, it becomes a tire rubber, and it becomes resistant to a lot of chemicals, solvent and all these things. So, this is what natural rubber is, and how it is the property of natural rubber is improved by cross linking with sulfur with the process is called vulcanization. Now, this is the story with natural rubbers post vulcanization went till 1939-40. During which the World War II was happening, and during World War II what happened, there was a shortage of these natural rubbers from the countries which I mentioned earlier. So, there was a huge requirement to make synthetic rubbers, so that we do not have to rely on the natural resources like rubber trees. So, at this time around 1939-40, where the first synthetic rubbers came in. So, synthetic rubbers are basically any vulcanizable rubber like polymer which is capable of getting stretched at least two times than the original length, and this stretching is reversible. Okay, so it should come back when you release the stretching, and these are mainly the synthetic rubbers are mainly of homopolymers of or copolymers of 1,3-butadiene and their derivatives and butadiene and its derivatives. Example as is first is SBR, which are styrene butadiene rubber. The example we gave in earlier Buna S, which is a 1,3-butadiene rubber with styrene, and Na was used for sodium, which is used for making the polymer. Seconds would be this polychloroprene rubber, where it is synthesized from the monomer chloropene. So, this is chloroprene, and you can get and this polymer is called neoprene. So, neoprene is basically polychloropene. So, neoprene is nothing but polymer of chloroprene, and this is neoprene is very resistant to vegetable oil and mineral oil. So, that is why they are used for in conveyor belt, gloves, gaskets and horses. So, these are some of the example of neoprene would be gloves, gaskets, horses and so on. So, you can read books or get this information from any other. These are just for remembering. The third category of synthetic rubbers is nitrile rubber. These are we are talking about synthetic rubbers or NBR, where we get a copolymer of 1,3-butadiene plus acrylonitrile. This is 1,3-butadiene plus we have know the structure of acrylonitrile here. So, you make a copolymer of this, and this copolymer I am not writing, I can write the structure. This is called Buna N. So, 1,3-butadiene, N for nitrile, and Na for sodium, where used for doing this reaction, and this is resistant to petrol lubricating oil, organic solvents, and this is it's used for making oil seal, tank lining, and so on. So, we talked about now natural rubbers and synthetic rubber, and the last I quickly go through in next 5 minutes is one important topic called biodegradable polymers. When we talked about polymers, different stages of polymers preparation and uses, we talked about that in the last step, which is very critical because nowadays wasting and the polymer waste is becoming a problem. So, basically managing the polymer waste which is not degradable by environmental conditions becoming problem. So, it is basically if we can develop new biodegradable polymers, it will be easy for us to handle this polymer waste. And by definition, what is biodegradable polymer? Is a polymer capable of undergoing decomposition into carbon dioxide, methane, water, inorganic compounds and biomass, predominantly done by enzymatic action of microorganisms like bacteria. So, basically it is decomposition of any polymer which gets undergoing decomposition into those ingredients, and which is mainly done primarily by enzymatic action of microorganism like bacteria. And carbon dioxide and water is produced when you do this decomposition in presence of air, and methane is produced in terms of when you do it in an anaerobic condition or in absence of air. And most of the natural polymers like cellulose, chitin, starch, proteins or polypeptides, they are all biodegradable enzymatically. So, so it is not a problem if you can make polymers from these natural polymers, they will be biodegradable by their own. The problem comes when we have we do synthesis from deals with synthetic polymers, and the synthetic polymers the aliphatic polyesters are generally biodegradables, degradable polymers. Example would be polyhydroxyalkanoates or PHA in short, and example is poly beta hydroxy butyrate co beta hydroxy valerate. In short, it is called PHBV. The structure is formed from 3 hydroxy butanoic acid plus 3 hydroxy valeric acid. I am not writing the structure because I have to finish in a minute. Valeric acid, and this gives you a copolyester, which we in short we write PHBV. The structure is you can write the structure yourself, and the other polyesters like polylactides, which are formed from polylactic acids or polylactides co-glycolides, which are formed from copolymer of lactic acid and glycolic acids, and polycaprolactones. These are the example of biodegradable polymers. So, with there are one example where you have the copolymer of nylon 2 and nylon 6. You can read from book. This is also a biodegradable polymer. So, what I will do, I will just quickly wrap up and I guess I should have, if I had 5 more minutes, probably I could have wrapped up it more nicely. But anyway, we have studied polymers, and if you recall the first lecture 1, we talked about that we will discuss these in this unit. What are polymers? We talked about polymers, monomers, repeating unit, and we gave enough importance that why should you study polymer, and we talked about different polymerization, different types of polymers, natural polymers, synthetic polymers, and branched, linear, cross-linked polymers, and the other type of polymers. And we talked about how do you prepare condensation, addition reactions, chain growth and step growth mechanisms. We gave you some common examples of polymers and their applications, and we also briefly touched on biodegradable polymers. I think with this I will wrap up this unit on polymers, and I hope you enjoyed this unit, and you can contact me in case you have any question, and I will be happy to answer your questions. Thank you.